Hi, welcome to the Physics Department's overview of the undergraduate program in physics. I'm Usha Sinha, Chair of the Physics Department. Shown on the left is a freshman mechanics lab in progress. Students work in two groups of two, and we emphasize hands-on training. Shown on the right is the weekly theoretical nuclear physics discussion groups. Undergrads, grad, and faculty participate, providing a great learning opportunity for our majors. Well, before we start exploring, let's see, why should I study physics is a question that might have crept up. A compelling reason is that physics has been at the heart of the most exciting scientific discoveries and technological advancement, helping us delve into our understanding of the universe to faster computers. Shown here are some images of the CERN project that led to the discovery of the Higgs boson, detection of gravitational waves, and the famous 1927 Solvay Congress with Albert Einstein and Marie Curie and 19 other Nobel laureates. Going on to the degrees that we offer in our department, we offer the BS in Physics and Chemical Physics, BA in Physics and Physical Sciences, and a minor in Physics. The BS degree in Physics has a series of core physics and math courses and culminates in a senior research. Within this degree, we have an optics track that requires the completion of 3 courses in optics. The BS degree in Physics has a series of core physics, chemistry, and math courses and culminates in senior research in physics or chemistry. The BA degree in Physics has the same series of core math and physics courses as the BS degree, but does not require a senior thesis. Further, there is more flexibility in the BA degree to select electives outside of physics, providing an opportunity for a broad background. Then last, we have the BA in Physical Science, and that is designed to prepare students for the single subject teaching credential in science and physical science. Completion of the physical science major provides the breadth needed for teaching interdisciplinary science in middle and high school, as well as the depth needed for teaching physics in high school. Then finally, we do offer the minor in physics, and this is often taken by majors in chemistry, math, engineering, and in astronomy. Now, going on to the courses and the roadmaps. So a list of courses you can best get in the general catalog, for which I've given the link here. So during the freshman and sophomore years, which is the preparation for the majors, you have the major core courses. You have the major core, and then beyond that, in the junior and senior years, you have the major core courses, the 3 electives, and senior research. We have 8 electives for students to choose from, and we'll also be offering 2 additional electives come fall of 2020. One of those electives is quantum computing, an exciting field including quantum mechanics of spin systems and qubits, entanglement, superposition, and measurement. And the other course is a lab course, the Condensed Matter lab. That's a hands-on class that includes synthesis of novel magnetic materials and physical measurements. The class is supported by a sophisticated teaching platform donated by Quantum Design, based on the close collaboration with Dr. Tarkachvili, professor in our department. Then let me highlight for you why you should study physics at SDSU. What's unique about our department? We are distinguished by a favorable faculty to student ratio that promotes a close and supporting atmosphere. We pride ourselves on hands-on labs, and our capstone lab, Physics 357, was designed by legendary Doc Morris and supported by a donation from CIMA. This lab was recalled by several alumni as the single most influential course in their lives. We continue to uphold this tradition. The BS majors are required to do a senior research project. This provides invaluable experience in doing research in a lab and often leads to publications as co-authors and prepares students for careers in industry and for graduate programs. So going on to the next slide, this shows a 2018 student presentation, which is the Senior Research Project Culmination presentation. So this provides students an opportunity to show to the physics faculty and students the research they have done as part of their senior research project. Then we have several resources for students for advising. So of course, we are supported by the excellent College of Sciences Advising Center. The link is provided here, as well as advising at the physics department itself. In addition to being the chair, I'm also the undergraduate advisor. Please feel free to contact me or the department coordinator, Ms. Marsha Queen, and the department website is given as well. And you can contact any of the faculty in physics with research specific or any other questions. Faculty names are provided in a later slide, and I encourage you all to reach out to them as well. So you would be wondering, students and parents, where a physics major can find a job. This pie chart from the American Institute of Physics tells the distribution of where students find jobs, as physics majors find jobs. 67% in the private sector, followed by 9% at college and universities, 6% at civilian government and national labs, and 7% in high school. So this is a broad area over which people can find jobs. In addition, the area of work is also may range from electronics, instrumentation, engineering, to computational projects. And in terms of salary too, physics majors do not do shabbily. The bar charts show that median starting salary, the dot, and the median salary after 10 years, that's in green, for physics majors is really competitive. So physics is right out here, is really competitive, ranking right up there with the engineering disciplines. It's important to keep in mind that physics gives a broad-based problem-solving skills that's more adaptable and creative to new situations, unlike even the engineering training. And if you want to see the placement of our majors, about half of our graduates pursue doctorate degrees, and the other half accepts employment in industry, national labs, and in education. And finally, no overview of the physics department will be complete without mentioning the vibrant and active Society for Physics Students organization, SPS. They form an incredible buddy system and pass on useful information to future cohorts. Information on summer research experiences for undergraduates, CalBridge programs, graduate programs, and application details. Further, SPS juniors and seniors also run a voluntary tutoring session for freshman physics courses. As freshmen and sophomores, you can attend these sessions as well as other support sessions available at the Math Science Learning Center and in the supplemental programs. The latter programs also recruit physics majors for paid tutoring positions. I strongly recommend for you to get to know SPS even from the freshman year. They can give you a great perspective on the physics program and certainly really useful survival skills. And let me add, SPS hosts a number of fun activities throughout the year. The following slides are a whirlwind tour of each faculty's research. So we have the following fields of research and faculty in those areas. Medical physics, 2 faculty, optics, 3, condensed matter physics, 2, theoretical computational biophysics, 1, and theoretical computational nuclear particle astrophysics and general relativity, 4 faculty members. And here's a full list of the 12 professors in the department. I strongly encourage that you contact them early on even as a freshman, to know what their research is. So going on to a brief overview of each one's research in the department. So we'll start with the computational theoretical physics, which is led by Professor Baljan. She's the only member in that group in this area of research. Professor Baljan's research group studies polymeric materials and biological systems driven far from equilibrium configurations by means of large-scale computer simulations. In addition, she's a member of SDSU's Viral Information Institute, for which she is building a large-scale simulation model of mucosal surfaces, which play a crucial role in our immune defense system. This image that you're showing here, that is shown here, is a snapshot of mucus simulation. Then we go on to the medical physics area of interest. One of the faculty in that is Professor Tim Basco. His area of research is in radiation biology. So his group is developing a biologically based detector to measure changes in DNA damage from different types of ionizing radiation. For example, X-rays, electrons, and protons. The idea is that this biologically based detector can potentially be used for basic radiobiology research or to help doctors know the biological effects of the radiation therapy treatment given to cancer patients. And here in this image, you can see one of the graduate students working on taking measurements on DNA while exposing them to radiation in this radiation treatment machine. Then the other professor in medical physics is me, Usha Sinha, and my area of research is magnetic resonance imaging. My focus within that is on muscle structure and functional imaging. So advanced imaging to probe structure and function of aging muscle include diffusion tensor imaging, magnetization transfer imaging, ultra-low TE imaging, and dynamic imaging. Here is shown an image of a student within the scanner at San Diego State University. It's a whole body 3 Tesla MRI scanner. It's an invaluable resource for research for physics undergrad and grad students. Then on to the next area of focus in the department, that's condensed matter physics. We have Professor Sundquist. He's presently developing his laboratory for studying quantum device physics at temperatures down to 0.01 Kelvin. He's developing parametric amplifiers based on superconducting circuits, guided by an understanding of their electrical impedance. Such amplifiers work near the quantum noise limit and can be used to read qubits for quantum information. And I'm happy to say that a dilution refrigerator capable of going down to 10 millikelvin is on its way to SDSU, slated in fact to arrive this week or next week. These are exciting opportunities ahead for our students. This lab will provide the training in realizing experimentally the theoretical concepts introduced in our new course, quantum computing. Then the next professor that is working in the area of condensed matter physics is Professor Torkachvili. His group studies the electrical, magnetic, and thermal properties of novel materials under extreme conditions. And the materials of interest that he studies are superconductors, magnets, and materials with topological behavior. Professor Torkachvili has also designed a new course that will be offered for the first time in fall 20. And the Versa lab from quantum design that will be central to his lab is shown on the right. It'll be a huge resource for both student teaching and research. And then we go on to the optics program in the department. Professor Kuznetsova's group focuses on nanophotonics or nano optics, which is the study of the behavior of light on the nanometer scale and the interaction of nanometer scale objects with light. It's a branch of optics, optical engineering, electrical engineering, and nanotechnology. Here in this image, you see one of our graduate students at the optical bench with a complicated system of lenses through which the laser light will be focused. Then we have Professor Anderson, who is the um, second um, professor in the optics program. His research is focused on ultra-fast laser physics, the interaction of intense fields with matter, and the shaping of short laser pulses in both the temporal and spatial domains. You can also see that he is the Senate Distinguished Associate Professor of Physics for teaching. And so part of his research is also on physics education, and it includes studying student engagement and interaction through video media, particularly with his novel invention, the learning glass. And you can see an image of the learning glass. Essentially, it permits the professor to write on the glass while viewing this audience, that is the class, and the students can see the writing the right way up. And then we go on to the last area of focus within the department, and that is the computational theoretical nuclear astrophysics. Here we have Professor Navarro Perez. He's the youngest faculty in our department. And he and his group engaged in computational nuclear theory, extending our understanding of the most fundamental processes in the universe, from the subatomic interactions that keep neutrons and protons together to the formation of gold and neutron stars. Computational nuclear theory provides deeper insight into these and other phenomena. Shown here on the image is the work of one of his undergrad students comparing their theory-based prediction to the experimental data. Then we have Professor Nolet. His research spans the interface between nuclear physics and astrophysics. He uses quantum mechanics to compute what happens in collisions of atomic nuclei. The purpose of this work is to improve our understanding of nuclear burning inside stars and in the Big Bang, and of the forces inside nuclei. So you see the figure on the right, which is shown here, and this is the production of the original chemical composition in the first hour of the universe. So right after the Big Bang, in the first 60 minutes, the production of different nuclei. And on the left side is the extrapolation of nuclear reaction data to the low energy where the reaction happens inside the sun. And the gray band is what the theory of Professor Ken Knowles and his group has come up with, a theory that predicts these variables are in this gray band. Then we go on to Professor Johnson. His work revolves around constructing and improving detailed computational models of the quantum wave functions of atomic nuclei, especially the use of these nuclei as laboratories to test fundamental theories of physics, such as the detection of dark matter. So many of his group's calculations are performed on supercomputers, and the group has close ties to several national labs where many of his students find employment. The figure that's shown here is a comparison of exact shell model, SM, and approximated projected Hartree-Fock energies. That's the model that Professor Johnson's group has come up against the experimental data of low-lying levels in iron. And you can see that the complicated and the more intensive calculation of the exact shell model actually matches very well with the approximated projected Hartree-Fock model. In addition, you can see that Professor Johnson is a faculty fellow Weber Honors College, where he teaches a popular course in the Honors College, Science and Science Fiction. So Professor Johnson will also be offering a new course in quantum computing in the fall of 2020, and this is a subject of intense activity across the globe. And finally, we have Professor Weber. He's a theoretical astrophysicist. His research focuses on compact astrophysical objects such as white dwarfs, neutron stars, and black holes. And you can see here that Professor Weber is listed as the Albert W. Johnson Distinguished Professor at SDSU, and that is only awarded to outstanding internationally recognized researchers. And that concludes almost all of the professors in the department and the different areas of research. So with that, I conclude this talk of the overview of the physics department. Please feel free to contact me or the department coordinator or any of the faculty for additional information.